accounted for. Thank you.
Hi everybody, good morning, and thank you, Chair, for introducing me. As we see, the topic for today's discussion, my presentation is driver adaptive and context-aware active safety systems using CAN signals. So in the last 2 days, we have seen a lot of presentations on context-aware systems, and we are also seeing a few on active safety systems. The key thing that I would like to introduce over here is driver-specific or driver-adaptive systems and the use of CAN signals more efficiently. I'll be giving an introduction on a basic introduction on how active safety systems currently are going to affect the driving scenario, some NHTSA statistics. I'll give a brief definition of what driver distraction is, and we'll look at driver and driving characteristic. I'll also introduce our project, that's a UT Drive project, system overview with the experiment and conclusion. So this is today's driving scenario. People do a lot of things while driving, a lot of infotainment systems, a lot of gadgets. Though the number of ECUs in the car, as the previous speaker spoke, the 80 to 100 ECUs in their car, many of them working on active safety systems. But still, you can't remove the driver from the loop, though there are automated vehicles and systems. As on date, driver is still an integral part. And how do you control that? People eat, people text. And also one of the major causes for driver distractions is traffic congestion. So I get stressed out when I drive, so I'm sure most of the audience here would get stressed out. So still, human behavior is one of the major causes of accidents in today's scenario. NHTSA estimates, these are some old estimates, but 20 to 30% of all the accidents that occur are due to driver distractions. And the last thing over here is 60% of all the cell phone calls initiated in 2000 were originated in a car environment. That's a huge number. And we have seen a lot of papers discussing on how cell phones affect drivers' driving behavior. So I would be addressing this issue. So we are heading towards driver distractions, and so I would like to give a basic definition of what driver distraction is, and also classify it into different categories. In the simplest or the most broad way of defining what driver distraction is anything that diverts a driver's attention from his primary task of driving can be termed as distraction. Visually, if you see anything that diverts the driver's eye movement for more than 1.5 seconds, the numbers could vary, but this is a humble estimate of 1.5 seconds, so could be termed as distraction. So the next step would be to identify what are the different types of distraction so as to handle these distractions in a better way. It can be broadly classified, our distraction could be broadly classified as visual, cognitive, auditory, or physical. All of these are not mutually exclusive, but they are dependent on each other. Say I'm speaking on the cell phone, it certainly is an auditory distraction. Also, it could be cognitive based on the kind of talk that's going. It could be physical as well if I'm holding the cell phone in my hand instead of using a Bluetooth or any other device. So various secondary tasks or tertiary tasks affect a driver, and it can be broadly classified into these broad segments. The next part, once we have understood what a driver distraction is, the next most obvious thing is to characterize a driver or the driving scenario. This is very important in understanding why we need a driver-specific or driver adaptive system and context-aware system. To come up with this, we started off with understanding how can we classify a particular driver based on Micon's hierarchical model of 1985. We did some modifications to it, and As this Cartesian space wherein we can characterize any driver into this space as a single point. It could be rule based, it could be skill level based, or it could be a strategic level knowledge. I'm from Dallas. I did my master's in Dallas, and I'm quite familiar with the road there. And I've been driving since the last 4 to 5 years in US roads, and quite comfortable with my car. So my maneuvering level, I can't consider myself an expert, but I'm neither a novice. So I fall somewhere in between, and my skill levels, my reflexes are pretty good, and I'm very familiar with the area itself. So owing to this, on a normal day, I would my specific location in this Cartesian space would be away from the center. On a given day, say now that I'm in San Diego and I hire a car, it's not my car, and I'm away from the familiar comfort zone that I have been in. So I go to unfamiliar territories, and I'm no more a novice driver, but I still tend towards being novice in that region. My skill level, even though my reflexes are good, the roads are different, so it would again shrink in. So as a point, the point would start drifting towards the center. I'm spending more time on this slide for the specific reason to address it to the audience that the driver is represented as a single point, and each and every driver would have his own specific point or location in this space. Each driver could be different in terms of whether they're aggressive, whether they're moderate, or whether they're very careful drivers. Once you identify what kind of a driver the person is, you could start looking at his or her specific patterns, and then go about to identify whether they're driving in a normal sense on a given day. So this is where we come to context-aware systems to understand what is the context in which the driver is executing his maneuvers. When we started off with our research, one of the main things that we kept in mind was to basically not add too many sensors to it. We tried to use the sensors that are already existing in the system. No better system than the CAN network, wherein all the sensor and actuator information are located. It's a different issue that car manufacturers are not open to give away information regarding this. So a lot of reverse engineering had to be done, and we pulled out CAN signals from the OBD port. And the bit pattern looks something like this, a lot of zeros and ones, and we had to do some reverse engineering, some hacking to figure out what are the signals pertaining to either vehicle speed or steering wheel angle or brake pressure. So we were successful to a large extent with the signals that we were interested in. The main point over here is the use of CAN signals, which are already existing, no extra hardware or required. And since it's already existing and all the ECUs interact using the CAN network, it's easily deployable. I'll just give this is me driving. I haven't edited the videos, so the plot that you see below is of the CAN signal for the entire route. This is me driving normally on Dallas roads. The pink one is the vehicle speed, the blue is the engine RPM, and the green is the brake, and the raw steering wheel and the corrected steering wheels are red and green respectively. So as you can see, I'm maintaining a fairly consistent vehicle speed. It isn't changing too much. I move from the rightmost lane to the leftmost lane, slow down a little, I see there's no traffic, and so I take a U-turn and I start driving further on. There's a curve coming ahead, and to do a curve negotiation, you see that the steering wheel is very gracefully turned. So this is my driving pattern. So certainly I'm not an expert, you can see that. So I complete one small section of this area over here without doing any tasks or secondary tasks. The next video is while me doing some secondary tasks. It could be something like texting someone, it could be like either pulling out some change for the toll or something like that. You can see the vehicle speed itself is not fairly consistent now. And the steering is also a lot too shaky. I was almost about to hit a curb in one of the regions. Still, I'm not a novice driver. I'm sure about that, but the point I'm making over here is when you do more than one task, when you focus on something else other than your driving, normal driving, then there are bound to be some deviations from your normal driving pattern. So also during at the same curve where I drove quite smoothly earlier, I'm actually drifting and I'm trying to correct it. I'm not totally out of control, so I'm able to correct it and go on. So this is the wealth of information that's there in on the CAN bus, the network itself. So careful use of these signals would be very useful. And short-term CAN signals are currently being used for in short durations, but a long duration would give a lot more information. I'll speak more about the project that we are doing. That's a joint collaboration between a couple of countries. We are looking at how secondary tasks affect drivers while either using the cell phone or dialogue system. Mainly, we are trying to build better human-centric active safety systems. So this is the instrumented car. We bought a Toyota RAV4 and we fitted it with 2 cameras, one facing the driver, one facing the road, microphone array and a closed-talk mic to capture the driver's audio data, and GPS signals, CAN signals, gas and brake pedal pressure sensors, which we later removed because CAN signals were able to do the same job, and then distance sensor. All of this was synchronously acquired using the data acquisition unit. We have 2 more tools. We have over 100 drivers data collected, so it's a huge corpus, and we need careful transcription to know what the tasks are. So this synchronously transcribes audio, video, and CAN bus data. Color-coded driving timelines are very important again in identifying how many tasks are being done by a particular person at a given time, and this tool would enable us in picking out that information. The system overview. To understand driver-specific systems, over here I'm using audio signals to identify who the driver is. The reason for me to use audio signals is this data can be also used for various other reasons to understand stress level of the driver. I'm not doing that over here, but in essence, that's the whole reason for using audio data for identifying the driver. Then I do a maneuver recognition. The reason for doing maneuvers is again very important. Like in speech systems, phonemes, words, phrases, and sentence which form a paragraph as such. Maneuvers could also be made up of small sub-maneuvers to maneuvers which would form multiple maneuvers in a route. So it's very useful to identify a particular driver scenario based on this. We use a GMM UBM framework, which is fairly common in the speech and speaker recognition society to use or to identify the driver, where with 20 hours of UBM data previously recorded and collected, doing some map adaptation for 8 minutes, we are able to identify a driver within 30 seconds of him starting to drive the vehicle. Once that person starts driving the vehicle, and now the next task is to do a maneuver recognition. We can use the same framework as GMM UBM framework to identify the maneuvers, but as a proof of concept, I would like to bring a simple FFT based system over here. The plot that you see here is a scatter plot with steering wheel angle, vehicle speed, and brake. As we can see, each of the regions are very clearly distinguishable from each other. A driver-specific system would help us in defining the boundaries, and for this is my driving pattern, and based on these boundaries, based on each driver, the boundaries would vary. I have a demonstration as to how we do recognize maneuvers. Along with recognizing maneuvers, the only point I would like to make over here is using a lexicon-like structure, understanding driver maneuvers. If I have to take a right turn, I slow down, I move to the rightmost lane, I hit my brakes, and then start turning my steering. So based on these particular patterns, I am able to predict a driver maneuver even before the driver intends to make a right turn. Even if the prediction goes wrong, eventually once the maneuver has been detected, I would be able to assess whether he is driving normally or in a distracted fashion. But predicting would be useful in assessing how the driver would be driving that particular section of the road. This is an unedited version of the video, so it's not so good. As a conclusion, the 2 points that I would like to bring over here is having a driver-specific or driver-adaptive system is very useful. It helps in pruning the data in the search space. It helps in improving the response time and accuracy of the system. Also, using CAN signals could not only give the current status of the driver, but also give what the next action of the driver could be. And also, these kind of systems could be used for driver self-assessment or parental guidance. Thank you.